Welcome to the Computational Design in Architecture 15th National Symposium, hosted by Istanbul Technical University, Graduate School, Department of Informatics, Architectural Design Computing Program, Faculty of Architecture, and Code Network in Turkey. We are honored to host Michela Turrin as keynote speaker today. She plays a very important role in terms of computational design research and education in our field. Please let me introduce her briefly. She is Associate Professor at the Chair of Design Informatics at TU Delft Faculty of Architecture and the Built Environment. Her expertise is computational design at the intersection of architectural design and building technology. Her ambition is to support architectural design innovation with engineering performance criteria by offering novel computational methods, techniques, and tools. She leads the section Digital Technologies at the TU Delft Architectural Engineering and Technology Department, also the research at the lab for additive manufacturing in architecture at TU Delft. She leads several granted and externally funded research projects and supervises PhD researchers and MS students. Her speech is titled Integral Design and Engineering, Computation at the Intersection of Architecture and Building Technology. Thank you very much, Michela, for being here with us today on behalf of our symposium organizing team. The screen is yours. After your presentation, I think we can get questions from the audience.
Absolutely. Thank you very much, Sabil, for the kind introduction, and thank you all for the invitation. I feel very honored to be here and be given the opportunity to give this lecture. I think you're seeing my screen by now.
Yes, we see perfectly.
I apologize. I go back one moment. I need to change the setting of the sharing as you were actually. Yes, it should work accordingly now. You see it back again, right?
Yes, we see it.
Okay, perfect. Thank you. Yeah, as Savi kindly mentioned, the topic that I would like to share together today and reflect upon is indeed the computation from the perspective of integral design and engineering. And well, what I mean with that refers actually to the complexity of architecture in first place. I look at architecture as a very complex system where inputs from different domains integrate. If we think of what expectations we have for architecture, and I mean we in terms of we as users, but also we as designers and as teams that work in architecture, we immediately can understand, I think, the very wide range of different, I call them performances that are expected. And don't refer only to technical performances, but also really to the qualities of architecture in terms of spaces, in terms of what characterizes the spaces, in terms of how we perceive them. And we want the space where at the end we spend so much time actually of our life within the built environment to be aesthetically pleasing, to be able to accommodate some of our preferences, but also to be well, technically sound in the sense of offer us comfortable areas, where comfort again is in itself a very multifaceted term, including visual comfort, acoustic comfort, thermal comfort, and so on. We want the space to be safe. And I don't name them all, I could continue forever, but this is to say the very wide range of features and expectations leads to the complexity of it, and also at the same time to the opportunities. Yes, the architectural process is something which is extremely complex, but because of this integration, it also offers the opportunity to use the drivers that comes from different angles and different perspectives to trigger the creativity, to innovate also in the quality of spaces. And that is eventually exactly where my, let's say, fascination for the computational contributions lies the most. I look at the contribution of computation, especially when we come to the intersection between architecture design and building technology, where I look at the engineering part, not as something that is meant to kind of be a post-processing of the architectural creativity process, and sometimes even be felt as a constraint, something which we need to go through unavoidably in order to make the idea become a true building. No, I actually really like to look at it as something which starts at a very early stage of the design and that can offer input and reciprocally iterate with the creative thinking of design in order to not only fulfill the performances that are expected, but even more to really help innovation, to drive the creativity toward innovation. And I think that the role of computation in this can be quite key. I specifically look at computation in this respect in its classical iterative loop between form generation, performance assessment, and what we usually call computational optimization. But in reality, I kind of embed within the term optimization a much broader meaning. I make a clear distinction between what we mean with optimization, what we are traditionally used to think of optimization for an engineering domain, where very often there are indeed kind of relatively focused numeric targets that should be achieved, in opposition to what in architecture is needed. It's nearly impossible to, or actually is impossible to, or would be very reductive to summarize an architectural approach in a clear optimization problem. It's never as focused as that. It is much more multifaceted, but yet the process can help, the optimization process can help iteratively in a process of design exploration. And this also means that beyond the aspect of optimization algorithms per se, there is a much wider domain of computational techniques that can be used in combination with a more traditional optimization process that is meant to help understanding the data that is being generated during the optimization per se, and especially to extract information from the data toward a deeper understanding of the different design scenarios that are being analyzed, and eventually even extract general knowledge that exceeds the boundaries of a specific design case, but that can lead to more general conclusions. Well, I will elaborate more in depth later on this part, but it's just to stress when I will use the word optimization, in reality, I would not want us to think of a simple optimization problem, but rather really to an iterative way of integrating the generation of data in the search of well-performing solution for highly performing buildings in an exploratory process that therefore is quite complex on itself. And I'm gonna think of this in the direction of a collaborative workflow. So what it is, I envision the user of these not as one individual user or someone that actually masters the entire process, but rather as a collaborative workflow where different disciplines act as specialists and are able to kind of integrate within this workflow, where the computational workflow per se is kind of one of the teammates, or at least I like to see it in this way. There is a collaboration that happens also between the designers per se and the computational workflow in architecture. With this specific standpoint, I will guide the reflection through, well, three main clusters, let's say, of brief examples, some coming from our students. And I would like to do that also because I think that the didactic part and education is something really important. And then in those regards, more the, let's say, the applications of these in terms of design application, but also in terms of design research. And then I will dive a little bit more in depth into advances that I believe are still crucial to be done and to be achieved within this specific approach. And this is more the work of our research team together with the PhDs. Starting from the design, I highlight the fact that we are really talking about kind of shaping the built environment in certain specific features. So I look at with the general idea of achieving highly performing buildings, performing in the very broad sense I just described, but on kind of case specific, so dealing with specific design briefs for certain cases. And I take the example of one master course we give. It's a MEGA, it's at the Faculty of Architecture, but it's together with students that come from the master track of architecture, of civil engineering in the building engineering track, and of building technology students. Students work in teams in this case, where each student within the team plays a specific role. The role of architect, structural engineers, facade designer, manager, computational designer, or climate designer, and they contribute to a design process from the specific standpoint of that expertise. So they are really kind of playing the role, which usually corresponds to their own master track, of that specific expertise within the entire workflow. They are tutored by specialists of the same discipline individually. And the entire idea here is to use a computational approach for integrating the different features of the collaboration. Students work on a kind of a BIM approach. We don't strictly follow BIM protocols, but the idea is focuses more on the principles of BIM. So they sharing a core model with different individual models that are handled by the different disciplines. What I want to stress for today here, in reality, we could explore more of different aspects of this workflow. But what is important for the point I want to make here is the integration within this collaborative workflow of parametric models, where students are kind of encouraged to capture the main features of their project, the nature, including certain design intent. So the idea of having parameters that would allow them to explore different design scenarios from the perspective of different disciplines. So with the idea of extracting data that would allow them to negotiate priorities that are different, possibly for different disciplines, in order to come to integrated design decisions in a multidisciplinary perspective. But the idea of also capturing within the parameters, and is something that is indeed not trivial, not only the features of the project that would therefore impact certain choices, discipline by discipline, but also specific design intents. How do we translate, parametrically speaking, qualities that are actually usually not numerically expressed? How can we capture that intentionality as well, so that it stays somehow part of the design evolution? Students are kind of encouraged to customize their own workflow time by time. So each team is actually would come up with their own collaborative way of sharing and generating models. But nevertheless, in each of them, there are kind of zoom in where the students dive deeper into this parametric and performance assessment optimization way for different features. Some of them are rather traditional, some of them are more advanced, but they are always kind of part of this integrated process that include multiple means, not only in the computational realm, but in any means that can help and support the generation and elaboration of integrated design ideas. So students go from very disciplinary optimizations, like in this case, we see just a fast sketch for the positioning of the outrigger within the entire structural system, or the very closed up definition of certain specific structural members within the entire structural system, or more integrating the aspects, such as the example of this case. This is all in the same project, where different features. On the one hand, the climate design, the energy generation from the PV panels, the quality of the daylight underneath, but also the structural consequences are kind of brought together in this kind of iterative exploration that are part of the overall process from the very early start. So we go through it in the initial massing of the project, for example, in this case, in the flora distribution, where the functionality is in relation to floor areas per each level of the building, the relation between the facade, the massing with the different functions that are distributed in the massing, or more into the detail phase of the project, where optimization in this case is applied for the configuration of the facade, again in relation to mostly climate-related features, but also the relation it would imply with the definition of collective spaces in front of it, or in case of complex geometries. This is an example where students were applying it for the definition in their project of the fin systems in the facade, therefore encapsulating also a logic of production. Now, this is just a very rough set of punctual examples, but the meaning that I want to bring forward is how students can somehow integrate, as part of this larger collaborative process, opportunities and options to inform, to generate data, to critically analyze them in an interdisciplinary setting, and to include them as part of their decision process, where the decision process is not automated. We are not like fully automating all the choices, but it's a constant collaboration between the team members and the information that can be generated, how to generate it, what does it need to be generated, and how to use it in order to support the decisions throughout the entire process. This is, by the way, a very short and compact course. Is a 10 weeks course, so it's also like kind of coping with the timeline. But and therefore there is also some limit, obviously, in the depth that the computational process can achieve. But nevertheless, what the reason why I'm taking it forward is because I'm very interested in how the dynamics across different students are changing based on the impact that this computational approach can have. The idea of being aware when making certain choices, rather than relying more on intuition or on tacit knowledge, but rather making that explicit and negotiable across the different disciplines. So the idea of collaborating based on actually data and information that can be extracted from that. If we go with the same approach, but kind of one step deeper, let's say, in a deeper level of understanding, we are working with students, especially in the master thesis, using the same approach, but then in that case, not specifically targeting one case, like in the case of, let's say, shaping a specific feature for the built environment, but really with the goal of achieving a higher understanding, something which can, let's say, be more generalizable, that exceed the validity of one specific case, but goes rather into general, let's say, sometimes guidelines, so knowledge that can be applicable in a broader range of different design processes. I take the example of few master theses just to give a hint of the approach we are taking in this direction. The main feature here is always the capturing of parameters that, instead of being specific, like we were seeing in the first case, where students are challenged to capture in the parametric model the specificities of their design. It is really about what, generally speaking, would impact certain performances. The specific master thesis deals with energy performance, and it's trying to kind of have the kind of as general as possible, including the parametric in the parametric models, a variety of different features that would impact the energy, but are completely unrelated. So you see, it's like literally generic boxes, let's say, being part of the same computational workflow, but then at that point with the goal of extracting data based on which correlations between input values, the input parameters, and the performance indicators, so the output values, can somehow be studied. We use this approach more as a research method, where it closely connects to data analytics, but it still uses also the optimization part, with the idea of gaining an understanding of what specific feature in the design process would make an higher or lower impact, and to what it is correlated, and what kind of correlation is there in relation to certain specific performances. This is being done, like in the first case, it was more on facade parameters and facade related feature for energy. In this case, it's for example, what impact as the height of high rise is on energy performance, and the option, the opportunity for high rises to actually meet energy standards, which are challenging in the case of high rise buildings, or does the layout actually have an impact on the energy performance? And yes, it does. There is also one of our PhDs working on this topic. What we see is actually a master thesis. The location of different rooms, the location of different spaces, how they come together, which is obviously one of the key features in the initial architectural composition, has also very high impact on the energy performance of the building. How can we correlate this? How can we make a designer being aware of what the consequences are, and how can we use this type of iterative processes to not necessarily have to run every time the full computational process, but eventually to gain a body of knowledge that can be placed upfront at the start of the design. We do this also in a more detailed phases of the design and cases, like in the greenery of the facade, and what parameters impact, in this case, not only the indoor climate, but also the microclimate that is generated outside, or indoor features of the facade, like in this case for its storage and the balance with certain economic features. Again, I don't go deep, but I just want to communicate the range and the breadth where this can be somehow applied, with, again, the intention in this case to challenge students to generalize outside the boundaries of specific cases, but rather understand the value of those processes as research methods to be able to generate a higher level of understanding and knowledge, they're applicable in multiple cases, and of course with the awareness of where this would be applicable, what are the limits of it, what is the validity of the information that is extracted that go beyond the value of the single parametric models that is created. Now, we have seen very roughly, but let's say some examples of applications in the understanding and in the shaping of the built environment. But nevertheless, what we are also, of course, extremely interested in is allowing advances of this method. It is already applicable and is already quite widely used also in practice, not only in academia. But yet there is still a lot that needs to be achieved in terms of research. I myself identify 5 main priority points. In reality, there are many more features that would require investigation and research. But the ones where our team is at the moment investing quite high attention are kind of those 5 main points. I will not be able now, of course, for time limits to dive in the depth of each of them. So we'll just briefly mention them, and then I take 2 or 3 to give some examples. The first one refers to the challenge in the parameterization part. The parameterization part is something which will determine what is the search space of any of those models. And it's far from being trivial. Being able to capture and to iteratively refeatures the parameters that are involved, and understanding what the relationship are with the dynamic nature of the evolution of the design process is something where, which is a key point, not far from being trivial, but at the same time, it does benefit from additional computational techniques. And I go far beyond the traditional sensitivity analysis, which still, of course, is one of the possible options. But we are looking at ways to extract and iteratively formulate the parametric models in a more dynamic way to accommodate the dynamic evolution of the design ideas. The computational burden is also something which is extremely well known and mostly relates to the heavy computational processes of simulations, usually, which is in most cases the bottleneck of computationally speaking of time-wise of the process. The understanding of large design data, well, we start always with the standpoint that sometimes having too much information and too much data is nearly as not having it, meaning one still needs to be provided with the opportunity to navigate the data. And what I find very fascinating in those collaborative processes is the different angles, the different disciplines would use in reading the same data. How can we provide and how computationally we can support the understanding of the different perspectives of the disciplines, but also the way in which they can read at best the information that is extracted from their own way of working. I will leave the other two for later in the lecture, since I will be giving some examples, and I just very quickly now show one PhD work that is dealing at the moment with the computational burden by, in this case, working with surrogate models, and is one of the possible approaches. We have other works that are working with simplified approaches and the option of speeding up the simulation, so working more on the simulation side to make them faster in the computational process per se. In this case, instead, there is kind of an acceptance of the computational time that is needed for the simulation, and rather trying to use them to generate surrogate models via machine learning. The PhD per se, well, the PhD is ongoing by Berkekici, is dealing with self-sufficiency in high-rise buildings. One example that is here is the challenge of having to cope with usually only a few standard floors that then are supposed to represent the entire breadth of the variation across the height of the building, which in reality does not always reflect what reality is, in the sense that there are very often situations that are quite diverse throughout the entire height, not only internally to the building, but also externally in the context. There can be obstruction, there can be elements that come from the surrounding environment that create localized condition that needs to be taken into account. So how to include machine learning in order to generate surrogate models to therefore at that point, on the one end, allow the designer to use this data, but on the other end, also being able to use them, for example, again, in optimization processes is something which is being investigated, is one of the key parts of this work. There are other projects, as I mentioned, but I just wanted to give a fast glimpse of what I mean with the work on the computational burden. Focusing a bit more in depth in the other 2 points. One deals with the integration of measurable versus qualitative criteria. This is something which I find extremely fascinating when we discuss about collaborative workflows. There is always a challenge in combining, so an optimization process, generally speaking, what is being computed within those exploratory design approaches is always numerically target. But there are features and qualities that are very difficult sometimes to quantify, and that still requires at the moment visual inspections in the geometry. The PhD that I'm showing here it is just finished. It was effected actually a few days ago by therefore one former PhD student of ours, Pavang. Deals exactly with the idea of allowing designers to combine and to be actually even able to choose which approach to take. Now, the specific case in which it is applied is the case of large sport indoor arenas. The parametric model in this case captures quality of the pitch, the surrounding of the ball for the spectators, the ring per se with the distances to the pitch and the relation with the structure, and a set of different structural typologies. The performances for which is being assessed are, in this case, a set of structural performances and a set of acoustic performances because of the multifunctionality which is supposed to happen in those type of buildings. I go a bit quick on these simply because the novelty, let's say, of the method per se is more relying on, okay, once let's say the generator is in place, and once the assessment model is in place, how can designer use them? And the approach that is being proposed here is it really provides kind of a choice to the designer, where the designer can either decide to prioritize quantitative requirements. In that case, and the multi-objective optimization is kind of driving the first set of generation and analyses, and any other follow-up explorations are kind of within the solution space of those models. The second workflow is intends to kind of flip the priority toward the qualitative aspects, and in this case we are using self-organizing maps as clustering way of categorizing the geometric features that are contained within the solution space. So we try to first make as broad as possible the parametric model in order to include a very large variety of different design solutions. So not to stream into the parametric part a limited subset, but rather to embed diversity in the possible solutions. And then at that point, not let any algorithm to first drive toward eventually a subset of these, but rather analyzing the entire breadth in terms of geometric clustering, a way of therefore providing a designer with families that can be explored, within which then certain optimizations can be run. And the third workflow, I don't go, of course, in the depth of each of them, but I only show the third one, is kind of trying to find a balance between the two, to prioritize with equal importance the quantitative and the more qualitative part, where in this case, the self-organizing maps is still being used to cluster the features of the geometry, and therefore to guide the designers into the understanding of the diversity and the families that are really being created in terms of geometric variation. But in connection with the performance assessment, which in this case is being determined with a neural network system, where therefore what the designer is provided with is kind of a landscape. It is not only the fitness landscape of the performances, but goes together directly with the geometric variation of the projects, of the design per se, in a really directly one-to-one interrelated way, and with a dynamic aspect of being able to kind of zoom in into each cluster of the geometry, and yet still being directly connected and aware of what the fitness landscape is for, well, in this case, a set of different fitnesses that were created, but again, that part is a part that could be changed depending on which specific design problem is being tackled. The idea here is really the one of guiding the designer, is the one of letting the designer decide also which aspect is eventually more important for the exploration, and trying to empower this collaboration between what is a decision that is still up to the designer, and what and the way in which the computational process can assist the designer in making those choices. I come now shortly to the last part, which is the interrelation with the materialization. So far, we've been staying kind of in the digital and virtual part, but we closely take into account in this loop also aspects of materialization. This goes in close connection with production techniques, and we obviously try to integrate the fabrication as well. And I will focus it in this case in one specific aspect of the fabrication, and the one that relates to the need of customization, not with the claim that this is the only possible direction, absolutely. We also take into account eventual cases of industrial standardization and so on, and rationalization of the geometry. But in this specific case, I decided to bring forward the example of what if the optimization leads into the complexity of geometries. Can we take advantage of new fabrication methods such as additive manufacturing to open up even more the freedom the designer has in order to explore diversity of geometries, and can we eventually use it also for customizing, so to overcome the limits of industrial standardization and rather be able to produce building components. In this case, we really narrowed down the scale into building components that would fit case by case the specificities that are needed in different designs. I will, and therefore we work very closely with additive manufacturing and our lab, LAMA, the Lab for Additive Manufacturing. I will just show a few examples which try to transmit, let's say, this idea of, on the one hand, taking advantage of this computational awareness of what performances are, and on the other hand, going together with form generation and tune the performances of it. I start with this project that regards acoustic. I will briefly show the first part of a video. Please give me a sign in case the audio does not go through.
Sure.
Acoustics are a rising concern in today's living and working environments. As function mixes and open or hybrid use of spaces are happening more frequently, it's important to find highly customizable solutions with little impact to the environment to target specific frequencies of noise nuisance.
In this project, we developed a digital workflow where designers, architects, engineers can actually craft acoustics and develop components that are optimized for acoustic performance.
The resulting design are then produced by means of additive manufacturing. We use additive manufacturing because of its potential to produce a large variety of complex shapes. It gives a lot of freedom in the complexity of the geometry, but also it allows producing pieces which are unique, meaning not necessarily based on industrial repetition.
The acoustic principle we are using is based on quarter wavelength tubes, and they absorb sound via so-called viscothermal damping. Inside the tube, a standing wave emerges, and that standing wave determines the frequency where sound absorption appears. The length of the tube and the radius of the tube both determine that specific frequency. Well, we can also achieve broadband sound absorption by including different kinds of tubes, so with different length and radius, in one product.
The computational optimization required a mathematical model. For this model, we used formulas from literature, which were anyhow not enough. Those formulas contain a specific absorption coefficient, which we derived and validated for a large set of measurements. Those were specifically fine-tuned for the case of 3D printing, which wasn't explored before.
Simulations, of course, are not enough, so we also had to do a lot of measurements. Typically, measurements are done in a reverberation room.
It's a huge room full of reflections, and by measuring in this room our sound absorbers, we are able to calculate their acoustic performance. the results are really promising, especially when it comes to lower frequencies. And we are really hoping that we will be able very soon to launch a ready product that can enter the construction industry market.
Let's skip this part and go toward the end where you can see the final prototype. Moving to the next slide. So we need to do it like this, I think. Yes. I will not at this point dive in the depth of all the aspects. I think that the video gave already the overview, but I just want to briefly mention some of the crucial points in reference to what I was explaining before. So there is a certain grammar, which is the parametric grammar, which in this case regards the features of these tubes that are connected to the acoustic principle. We talk about the length, the diameter, the amount of openings, so the porosity of the final surface of each specific tube. And this is kind of connected in an optimization loop, in this case, targeting as high as possible absorption coefficient for the final element, which therefore gives the number of tubes and their combination of radius and length is. And we have an automatic system to kind of lay down these in different layouts where the designer is free to give any type of starting surfaces in a shape. Now you see the very simple example of a circle or an hexagon, but in principle it's any type of doubly curved surface as long as an offset principle is applicable. And we therefore automate the generation of those elements, trying to give on the one end the guarantee that this specific frequencies that have been chosen at the beginning as target frequencies, which could either target one specific area of frequencies because of a certain specific acoustic challenge. We've been working with case studies on cabins, for example, where there are definitely certain specific low frequencies. But we have been also working with case studies where a much broader range of different peaks was intended to be achieved. So one can somehow tune the final acoustic effect that is intended, and at the same time come up with geometries, but also giving the designer the freedom to explore and to be creative in a different type of shapes and panels and configuration that can be produced. We have been working on the one end, for example, with the idea of saving as much space as possible. This system is very effective also in low frequencies that usually in traditional acoustic absorption requires kind of rather high thickness of absorbing materials, whereas in this case we can achieve that with very thin elements. But we've been also working with extremely sculpting, let's say, elements, so where space was definitely not a concern and was instead being used as a representative. Like in this case, for example, kind of sculpting acoustic element in spaces. A similar approach has been taken also in this project, which regards, in this case, thermal performances. Here the level of automation in the optimization workflow in the form generation is lower, but the principle is similar. So there are drivers that come from certain thermal principles that in this case regards the heat storage capacity related to phase change materials in a container that is meant to act as a thromb wall within indoor spaces, which is then tuned in terms of geometry to activate principles that would enhance the behavior of the material per se. Therefore, a sort of optimization that even though, as I mentioned, we don't have like a full tool that would support this yet, but that has been run in order to define the form finding in connection with consideration that come from the fabrication requirements, and the structural stability are of course involved in the structural stability part especially, led to then the definition of a first prototype. If you see some close-up elements of it, and the installation for monitoring in one room of the Green Village at the TU, where the thermal behavior is now being monitored. And so on and so forth. There are similar projects, and I don't go into all of them. I just want to stress that sometimes we collaborate with practice, which is also something that I find extremely important and valuable, to have directly involvement of architectural ideas, where we see how the team of the design and the external architects in this case can directly interact with the form generation, and again take advantage of additive manufacturing in terms of freedom. You see the PULS project done by a large external team together with our team as well, for shading elements. There would be several other examples possible, but the entire bottom line of all these is really the opportunity that that combining optimization together with additive manufacturing opens. And I talk about opportunities for the designer, but opportunities also in terms of performances, in being able to integrate different performances in kind of monomaterial elements that can, at that point, result being multifunctional. But again, also stressing that is not only a matter of taking advantage of the freedom that such a new production technology can allow, but is also a matter of capturing the knowledge that is needed. Additive manufacturing still requires, as constraints, still requires quite some body of knowledge in order to be able to use it at best, to be able to be effective in actually saving material, in making the production being feasible, in easy assembly of the parts, and so on and so forth, which can be again captured in the models for the optimization per se. So once more, I want to stress the close interrelation between the elements, also to inform back the optimization per se. Coming now to a conclusion, back to where we started, what I want to stress is that across all the different examples, and including the main research points, I think that one of the core messages that I really like to look at is how this is a storyline that is really in progress. There are new potentials and new opportunities that are very quickly opening up, and the designers are provided with. So I really like to look at this as a work in progress, where we are all contributing to its development. And in this respect, I'm really happy to have questions and to have a little bit of debate and sharing reflections with everyone.
Thank you very much, Michela, for this enlightening lecture. It was excellent, I think. Now we can get questions from the audience. You may also use the chat to write down your questions.
And shall I stop sharing? Perhaps is the
yes, yes, sure.
We see each other.
Yes, it's better. So, is there any question?
I raised my hand, but it's lost in the yellow of the background. May I?
Yes, yes, sure. No,
Thank you for this fantastic talk, Michela. It's always a pleasure to look at your work, first of all, and it's so nice to see you. I've been thinking about, as I was listening to you, and I am familiar a little bit with your work, and also the courses at TU Delft over our short-lived joint program adventure from years ago. I'm trying to phrase a question, but also I'd like to get your actually basically just opinion on the matter. For a long while at TU Delft, you've been working with mega scale projects. I mean, pun intended, maybe, I don't know. I remember the big and tall workshops, and you showed some examples, and now this mega course. And firstly, what you showed in your sort of framework for us to comprehensively show us the research at hand. It seems to be dealing with mostly large-scale projects, but then you also have very nice examples such as Adam or Double Phase 2.0, where it comes down to another scale, the building component scale, where we can think about a different scale of design problems, not the mega projects with big data driven processes. So maybe two questions. One, so the framework does apply to other scales as well. So this complex computational processes apply to smaller projects too, maybe in your mind. I'm curious. So for example, low cost projects or more humble projects that we might be seeing more in the future because the world is becoming such a hectic place, right? And also, do you think about or calculate the economic feasibility and sustainability of these computational methods? Thank you.
Yeah, thank you, Mina. And yeah, I share the pleasure actually to see you. It's really nice to see you here, and thanks for the invitation once more. Yeah, you're touching, I think, really extremely relevant points, and those are in part also our own points of reflection and questions. So I might not have a full answer on all points, but I'm really happy to share my reflections on these. First of all, on the applicability of different scales, yes, I do think so, in the sense that what at least I'm fascinated, and what we are trying to capture in the computational approach is really like the dynamic that happens in terms of different priorities and in terms of different features that the design needs to include. Now, yes, it's absolutely true that we started and we worked a lot very often with extremely large scale projects. That I think is a domain where this comes to an extreme, in the sense that is a very evident and quite, let's say, well-known challenge in terms of complexity, in terms of different parties that are involved in the project. So it did offer at the start a very fertile ground to test and experiment with this approach. The small scale components is something which more and more, especially when it comes to the search of high-performing components, which are tuned to certain performances, at that point has kind of the same level of complexity. The scale is different, but the dynamics of the collaboration, the dynamics of the interdisciplinary feedback, and how information from different domains and different disciplines needs to come together in one specific development of the process has actually very strong similarities. So there is a very strong common ground between these extremely large scale and these small scale for elements that are very high performing on certain features. Now, coming to the point of, let's say, more standard project or affordable projects and so on, absolutely yes. Let's say, I think that there has to be a balance also between which decision and which information is needed to take certain decisions and the complexity of decisions that needs to be taken. I'm not advocating that anything should be parameterized and subject to very complex computational workflows. But if it is needed, if there is a benefit on that, if there is a doubt, if there is something where the knowledge of the team may require a support in the integration, then absolutely yes. So I think it's really more, it's not a matter of not being possible. I think it is absolutely possible to apply it. It's really a matter of balancing the effort that is needed for the computational setup versus the benefit that can be extracted from it and how much is needed. On the other hand, I also stress that the computational part is evolving very quickly. So what a few years ago was kind of challenging to set up, nowadays is really common and easily applicable, and I expect that to speed up even more. So what we see now still as perhaps not fully worth, let's say, in terms of effort to apply into certain projects, most probably they will become quite fast and easy to apply in the very near future. So I think that the two things will definitely come together. I don't know if I answered your question, but that's
Yes, thank you, Michela.
Thank you. Is there any other question? I don't see it. I just check. Okay, if there is no other question, I might ask one if it's possible.
Actually,
so you, yes.
Actually, I had, but I think it's a
Okay.
little bit difficult.
Sorry.
Hi,
Please
Michela,
go
how are
ahead.
you?
Hi, very fine, thank you. I hope you too.
Yeah, thank you very much. Actually, maybe it's not a real question, but it's a kind of reflection as well. I was just looking for and, noting what you are saying about the research fields. And I think in coming years, we will talk more and more about two things. It's the data burden, not computational burden, but I think data burden will be a real matter. And I think the most challenging part will be the formulation of the problem. And it's getting more and more sophisticated and more complex and more and in that sense, the scales are actually melting to each other. And I think what Mine is saying and what you are saying is the signature for the coming years. And in that sense, your examples are excellent. But what I would like to ask to you is, for this data burden, together with this computational burden, what are the new skills for your students that you would like to expect to have? Because we are offering many new courses and we teach them all these machine learnings, etc., etc. But for you, for example, what is the survival skill in this new burden?
Yeah, that's indeed a very good point. I like this reflection. I think that so yeah, I agree on the overwhelming let's say amount, but also different direction that data is taking. Still, in any case, I kind of like to look at it as an opportunity. So I agree on your kind of survival scale that is being pointed out. But at the same time, I kind of look, so on the one hand, I think we really need to face the reality of organizing the data and on being able of, so there are questions that when we talk about data that really exceed the nature of the data per se, but that touch a very wide range of different aspects, from ethics, from privacy, from open data versus closed data, from all those type of very, I think, relevant and crucial questions attached even to the nature of data per se. So that to me is something which is equally important. Is not the data per se, but is really what it entails and what effect and impact can have even eventually on new economic models. Who owns the data? Who owns the information? What do we do with that? So this is really like an immense terrain for debate, and that we absolutely need to shape for the future. It will be crucial. But then, technically speaking, within this, I think that like in the computational part, we can definitely again have opportunity. First of all, to storing the data is already a challenge. There is no doubt that data storage places nowadays are something which is under the hotspot, also in terms of sustainability. So we will have questions there as well. But even assuming that this is so, that we are simply provided with all this data, then the ability and the opportunity to stream them, to use them, to organize them, to connect them to the future where they can really be informative, is something which is indeed extremely complex. And that, I think, is not let's say, the role of or the task of one specific standpoint only. So yes, computation can definitely do a lot with that, and I think we are all working in that direction. But I really look at it as something which needs to come from different parts as well. Policies, ways of working, like organizing the information. And at that point, it does not regard anymore only the information that is generated during the design process, but it regards also the information that is attached to the use of the building, at the operation of the building, the use of how the users use it. What do we do afterwards? Data becomes extremely important also for circularity. How do we attach information during the lifetime of the building to the element in order to make an assessment for its end of life, for example, and so on and so forth. So it's something which well, I do believe computation has a big impact, but it's not a one-way impact. It really needs to come together with those, with all those policies and all these different stakeholders. And I think that a key point is really the communication and the awareness that we need to have together with them. So I don't have a scale, let's say, to really tackle that, but I would again instead divert toward the collaboration and the awareness of how do we need to do this together with different parties. And to me, also for the student, it is something very important to be aware of, in my view.
Thank you. I would like to ask one question, if it's possible. You presented very exciting set of work. I know that you're also involved with some research projects with the industry and practice. So my question is, how do you see the future as an educator and as an architect in general? Somehow architectural education and practice, they still maintain their conventional nature in terms of design and production processes. So what will be the required skills and knowledge of architects in the next 10, 15 years?
Yeah, indeed. Yes, we definitely work, I agree with you, we work in a rather conservative field. Architecture tend to, also because of its complexity and all the integrated parties, tend to keep working how we are used to, which might be acknowledged, not be perfect, but it's kind of in practice sometimes an easy way to proceed. But nevertheless, I think that at least we see here a very increasing trend in change. Big and large firms we collaborate with, they do have internally, all of them, a computational research department where definitely there is a key driver in taking advantage of new computational approaches, but also the small firms. And there I really see how our students, or I talk about ours because are the ones that I know and I have attended in terms of examples, but I'm pretty sure it's the same for anyone working in this field. They kind of plug into realities that might not have the previous experience in terms of computational workflows, but definitely they are welcomed and step by step have an impact on that. So I actually see that as evolving quite quickly, at least in terms of design process, in terms of construction process, building process, and so on. Then of course the complexity is higher in terms of, well, there is also the entire infrastructure of how industry works. So I see a bit of a difference between architecture and engineering firms versus really like industrial production of what entails the building industry. But again, like I see that there the innovation is more on a step-by-step and localized targeting specific challenges. We do work, for example, just to give an example, with a very large facade producer that has now in-house a set of a line for the additive manufacturing, something extremely new for them, which wasn't there a few years before, but that is now becoming kind of a common stream as well. And again, I don't necessarily advocate additive manufacturing as the solution for, but I take that as an example because I think is representative for, on the one hand, the complexity of it, on the other hand, is high-end, is expensive, it has really like quite some challenge that is attached to that, and therefore is not necessarily the easy solution for many cases. And yet, even in that case, we see a trend in dropping down cost as well as easier integration in industry. So again, I don't have really a clear answer, but I do think that the direction will remain the one of a much, obviously I'm saying something obvious here, digital workflows and digital production, but the timeline might also surprise us on the speed. I'm not very skeptical on these actually.
Okay, thank you very much again for your valuable contribution to the symposium. If there is no other question, I can close this session. Is there any question? I don't see, I just checked one more time. After a small break, we will continue with the paper presentations in the session 1, titled Computational Design Process and Creativity. Thank you for your participation.
Thank you very much to you and to you all. Big pleasure, and I hope to be in contact soon with everyone.
Thank you.
Thank you.
Very much.
Thank you.